So my name is Maria. I am a kind of like last year PhD student at Purdue. I work mostly on natural language processing. I'm part of the NLP group here at Purdue, and my work kind of focuses on joining kind of like the neural models that everyone's hyping over recently with traditional symbolic models of AI and knowledge, kind of like the intersection of these two things. We're mostly on Discourse, but I did collaborate with Max and other people at Northeastern on kind of like using NLP for security applications and networking applications. But this work that I'm going to present is on kind of like a general framework that we developed, and it's kind of the crux of my dissertation. And it's a bit about, like joining these two ideas. So I'll go ahead and start. So natural language processing has been barely overcome by deep learning in the last decade or more. And the adoption of these methods has made, like impressive and unquestionable advancements in the last decade across all NLP tasks. These approaches try to do this kind of like what we call end-to-end learning, where they try to map inputs and directly to outputs and think about kind of like a classifier. And the idea here is that instead of, like before, people would like really model, the structure and the features of what they want to do. In this case, they want to basically map the language to whatever output they want to do and let the neural architecture kind of take care of everything by embedding the structure of the language in a hidden high-dimensional space. This example right here is kind of like a fun example from one of this like large-scale language models that has been released recently. And it's a kind of pretty impressive by responding to common sense questions. However, this method does come with some drawbacks. They can be really hard to train basically because of two reasons. They have tons of parameters. So if we look at this graph down here, this is the number of parameters that they've grown for language models since the introduction of BERT. BERT was like a big transformer model that Google released, I guess it was 2019. And it was already huge. And this has kind of like grown exponentially with time. So basically these are like millions and millions of parameters. And to be able to train something like this, you need massive amounts of data, right? So we're talking about, like these are industrial scale language models that are trained, by big names like Google, Microsoft, and OpenAI, and so on. And so this is not something that's accessible, to everyone to handle this amount of data. And then they have their downsides, right? So while it can be pretty impressive, recent work has shown that they can make inconsistent predictions, they make shallow associations, and they're essentially unexplainable black boxes, right? So they memorize this data, to fine-tune tons of parameters. And then there's like a big body of work now on just trying to like open this box and try to explain what's going on inside. On the other side of things, before AI in general and also NLP used to use symbolic inference for most applications. And this is usually a more natural way to express and reason over problems. And the go-to example, it's like if you have tons of data in a knowledge base, then you can make sort of inferences or derive new knowledge from what you have there. So if you have, the fact that all people are mortal, and that Socrates is a person, then you can infer that Socrates is mortal. A lot of work has been done in the past on learning these models from data and dealing with uncertainty. And probabilistic graphical models are one of the tools, or one of the like modeling paradigms that was used a lot to model dependency between different decisions. So it's kind of like, you have this factor graph where you can encode dependencies between different variables and then be able to model a lot of structure. And this was very used a lot in NLP before. One good thing is that they're interpretable, right? So, you model directly the dependencies between the different variables, so what you're modeling, and introducing domain knowledge is pretty easy, unlike in neural nets, right, where everything's kind of like a black box. On the downside, they're less expressive, particularly when you're talking about something like language that is really high dimensional and noisy. If you were to like create a symbol for every like word form or pair of words, triples of words, the more context that you want to introduce, this kind of like starts to explode. So it's not necessarily feasible. I see someone's trying to join. Max, can you see it?
Yeah, I got it.
Yeah, yeah. So why not, like join the best of both worlds? So you can have the expressivity of neural networks, but the interpretability of symbolic methods. So this is kind of like what we look at. So if we look at a traditional neural model for language, you usually have like, a snippet of text. In this case, this is a statement by Vice President Kamala Harris, and then you run this through a model, and then you want to like draw a prediction from this. In this case, whether this argument was pro-choice or pro-life. When we talk about how to, like introduce neural symbolic methods into problems like this, what we want to do is learn to decompose the decision into kind of things like can be symbolic abstractions of things that we want to model. So in this case, think about, explicitly model who the speaker is, what a stance is, also the text, right? So you can have the argument made and maybe some entities that are being mentioned in the text. And then kind of that allows you to introduce, symbolic relations between these things. So you can do something like, oh, the speaker is making this statement, this statement targets this entity, and this argument has this stance. And then this allows us to kind of like do some reasoning over the symbols that you can explicitly do if you were to just use kind of like an end-to-end model. This is on this space is pretty, your standard symbolic models. There was a lot of work done on this kind of things before, but how to introduce, neural components into this, then what we think about is then use neural nets to learn representations for the symbolic components of this thing. So you not only have a symbol of an entity and a relation, you're going to have, an embedding for this that is learned using a neural architecture. So now you have a vector, that represents this symbols, and then you can have both the neural representation and then the symbols to reason and do inferences over this. So this is kind of the pitch for this. Obviously, this is a hot topic right now. Some people are looking into this, but usually when the NLP crowd looks at neural symbolic models, they tend to stay in the usual suspects. So things like, knowledge bases are a natural fit for a model like this, because you already have the entities, you have the relations, and then deriving, rules, do some induction, this kind of thing. It's pretty common. And then traditionally from that flows, keep question answering, because you're then trying to do like this multi-hop reasoning over knowledge bases. And then language grounding, when they like ground things in vision, robots, this kind of things are pretty, your usual suspects to do with something like that. But in our work, we try to motivate this for discourse problems. And when we talk about discourse, we're typically talking about things where, you're looking beyond the sentence boundary. So you have one or multiple long texts. This can be post, documents, tons of things. You also have repeated concepts and talking points that you can model and create symbolic abstractions over. So the example here is like, well, you have a debate between, Vice President Harris and Vice President Pence, and they're, making some particular points that tend to be repeated. So when they talk about women, poor women or women of color in the context of abortion, or when they talk about, babies, the unborn in the context of abortion, these are things that keep coming up, or things like Democrat, Republicans, who these people are, what parties they belong to. These are kind of like things that come into play. And then we have structural dependencies between the different talking points, the different concepts, and the broader context, right? So the way people construct arguments is something that, exists. The way you can build up an argument is very structured usually, or like turn taking in conversations. These are all types of structure that you could model. And then the broader context, as I say, right? So language doesn't occur in isolation. There's something that goes beyond that you could explicitly model. So who these people are, the party they belong to, their relations to other people, bills they sponsor, bills they co-sponsor with other people. Those are tons of things that you could kind of consider when talking about discourse. So the contribution of this paper that I'm presenting right now is a neural symbolic modeling tool that is declarative, called DRaiL, that can do the following things. So integrate expressive textual representations. So, take all of these things done in like BERT and all these language models that are out there, they work, they're expressive. Can we incorporate them, easily? That's one thing that we do. The other is support structure prediction across long text. So when we talk about structure prediction, we're saying that instead of predicting just a single label for a problem, you're predicting a structure. So could it be, like a sequence or are a tree, this kind of dependencies. And then combine several modalities in the representations. When we talk about modalities, these are just different types of inputs. So text and images could be two types of modalities. Text and social information could be two types of modalities. And then produce models that are more explainable than end-to-end models, and that you can explicitly leverage domain knowledge. So for this, then we present DRaiL. It's a general purpose declarative framework. And what we can do here is specify complex NLP tasks by breaking down the problem into domain-specific atomic components. So think about the example that I gave you of the speaker, the entities, the argument, the stances. So these could be atomic components. They could also be things like just as words, sentences, paragraphs. It depends on the level of abstraction that you would like to work with. And then you can also specify dependencies between them, their properties, and other contextualizing information. So it's this idea of creating these relations between entities and then rules over these relations. And then at the same time, you can define any neural architecture to embed these concepts in these relations. And we provide this using, you can use PyTorch, which is like a common deep learning framework that everyone uses on Python. And then you can just kind of like plug in any type of architecture. And now you have two ways of representing dependencies in your problem: over the output variables, like symbolic models do, and then over the neural representation in a shared embedding space. And I'll get into what this means. Kind of like the broad overview of the DRaiL before I go into the specifics. So you have an input, a model that you want to, a domain that you want to model. In this case, we'll go back to statements made in debates by politicians. And then you can kind of like extract or define entities and relations between them to learn representations for the symbols. So you can learn embeddings for, the entities that you care about, stances, the speakers, the text, and then other things like voters, parties, and then relations between them. So now you have kind of like this shared distributed space where you learn representations for these things. And then you can combine these embeddings in neural scoring functions to learn weights for kind of these rules that you can define, and then kind of like perform kind of like a weighted symbolic inference, where you have kind of like weighted rules that define a particular structure problem. This is kind of like the broad view, and going a bit. And it's the key component that is that once you have these weights, then you can keep training your model, both by learning better weights for your rules and by kind of updating the internal representation of these entities. Obviously, as machine learning models go, you usually have ground this in data. You have some training data that you can use to kind of refine your model. So this is kind of what DRaiL does. So we have a little language that you can use and a grammar to express problems. So you can define entities, relations, and rules. Rules are written in kind of like clausal form. So you have a conjunction of predicates, an implication, and a single head predicate. And this way you can define dependencies in your problem. So in this case, we were modeling a debate. So we have, we call it user. It's a user that comes into an online debate and debates something. T is the topic. And agreement is agreement between users and text, users and users. And then we also have other users that come and cast votes for the people that they agree with. Think of this like a like on Facebook, more or less. And then you can define dependencies, for example. So if a user agrees with a topic and another user votes for that person, then that person agrees with that voter, right? So you can kind of define these dependencies. So you have an input layer, right? That is exactly these entities and these relations, and let's say some arbitrary input representation for them. This can be, any type of feature that you would like to consider. It can be, word embeddings that were pre-trained in some other model, anything goes. Then you can, we have what we call this like RAIL nets, or the shared embedding space, where you define kind of like modular encoders using neural nets for this different components. So you have a way like a user or a text encoder that you can reuse, and then relation specific encoders. The reason this is shared is because the same entities and the same relations are going to be used by multiple rules, right? So the idea here is that you reuse the same parameters every time a user or a relation appears in the problem. So this way you learn kind of like a global representation for users, tags, or whatever entities you're representing. Then we have the rule layer, which is just another scoring function on top of the embeddings of entities and relations to derive the weights that you're going to have for each rule. So in the end, you're going to learn a weight for each of these rules. And what this does is defines a factor graph of dependencies, where each rule defines kind of a dependency between the open decisions. So for example, in the rule below, the dependency between agreement and voting could be one of these factors, and this is going to have an associated weight to it. So the task that we have is, learning the weights that satisfy our dependencies and better kind of like learns to predict the data or domain that we have. So to kind of formalize the DRaiL program, rule groundings, as I told you, rules are basically this kind of like implication style rules where you have a conjunction implying a single head predicate. So you can rewrite this as linear inequalities corresponding to their disjunctive form. And then you can easily turn this into a linear program that you can kind of solve. This has, like performance considerations because this is an NP-hard problem, right? It depends on the type of dependencies that you will have. It'll be intractable, but there are tons of relaxations or kind of approximations that can be used to approximate this model. And then each rule grounding defines a potential that you add to the linear program. And we also provide the option to provide what we call hard constraints, which are going to be unweighted rules that always have to be satisfied no matter what. So then in the end, you can define a map inference problem over the set of potential and constraints. And your task is to, maximize this function, right? To learn the weights for all your rules. So the neural components, kind of like formalizing that, is that each weight of the rule is going to be given by a scoring function that is basically a neural net. And you have, parameters for each neural component, for each rule template. So each rule basically is tied to a neural net, and then that is decomposed on kind of like relation-specific and entity-specific encoders that are then reused by all rules. So this is kind of similar to other ideas that are common in the machine learning community, like modular architectures or multitask learning, where you kind of learn to learn parameters across multiple different decisions. In this case, we can think of the different decisions as being the different rules. The main difference here is that now you're going to have kind of like an inference procedure that combines all rules, considers all dependencies and constraints, and then backpropagates back to the neural components. So you learn kind of a representation that's kind of constrained, right, according to the type of model that you learn. So the goal of this is to capture properties that are unique to their types, for the different entities and relations, and then relational patterns that learn to contextualize these entities. So we make the distinction between entities that are raw or symbolic. So you can have, an entity being a sentence or a document or a paragraph. So that's going to be, associated to some raw input representation, like just the text. It can be a user with some like features that you would like to define in a profile and so on. Or they're strictly like symbolic entities, like an ideology that you're just going to learn a particular representation for. And by doing this, we are going to support this type of operations to move between symbolic and embedded or raw information. We call this kind of like embed symbol explain data to align the representations between symbolic and raw entities. So you can, for example, push the representation of a text closer to a symbol that defines it. So let's say I want the embedding of the ideology, liberal or conservative, to be close in the embedding space to statements that are made either by Republicans or Democrats and so on. So this way you learn representations that kind of inform each other. And then in the symbolic line, we have this translate correlate, which is basically aligned representations of pairs of either symbolic or raw entities. So let's say, aligning the pro-choice embedding with the liberal embedding, for example. That's one thing that you can do there. So to talk a bit more about this, this is kind of what we ask when we talk about this representation learning objective. So embed symbol is, can we learn a meaningful embedding for a symbol? like liberal conservative. Explain data is to map raw textual statements, for example, to meaningful symbols. So statement to ideology. Translate is represent different modalities in the same embedding space. So two things that are attributed like a statement and a user. And then correlate, as I mentioned before, something like ideology and stance would be an example. So learning is done. This is a kind of a, there's nothing new, in the learning component of this. We borrow ideas from what is structured prediction or structured learning in NLP or in machine learning, which is, you're instead of learning a single output, you're learning, all of these rules and their dependencies. So you have, all of the rules tied to a particular neural net. You derive all the scores. Then you wrap the map inference procedure to find the best assignment. Then you have, your global structure given by your training data. You derive a loss function between the two of them, and then you backpropagate back to everything. So there are tons of loss functions that can be used for this in the literature. We've experimented with a few in the paper, and they'll have, this pro and cons depending on how hard it is to approximate, this type of things, because depending on what your structure is, this can be untractable. One that we worked with is the structure hingeless, which is pretty simple. In the end, this is just the difference between the goal structure, which is the structure given by your training data, and the score from your highest performing current model given by your current parameters, which is just the prediction that you have from your current model after running the inference. So, and then, add in some Hamming loss to add some sort of a margin. And Hamming loss is basically just the difference between the gold structure and the predicted structure. Usually some one whenever there's a match and zero when there's not. So this gives you kind of like an augmented loss. Loss is obviously going to be zero when the goal structure and the prediction is the same. So then you don't need to know anything if you make perfect predictions. But if not, then this is going to grow, right? So the more different they are, the higher your loss is going to be. And then the objective is to bring this loss down. So learn parameters such that this loss comes down. So that's kind of what the framework does and how we set it up. And then I'm going to show one evaluation. We've done tons of this for this framework, different domains. In the paper, we have 3, but I'm just going to walk you through one. So this is a task that we call open domain stance prediction. So basically you have a discussion, think about a debate online. So it could be on Facebook and Twitter. So someone posts kind of like a topic. In this case is like, those private gun ownership deter crime. That's the topic. And then people come and comment on it. And people jump in, they disagree or agree with each other. And the task is to predict whether each of these texts agrees or disagrees with the main question being posted. So we turn it into a structured prediction task by predicting both the stance of the topic of the post with respect to the topic, and then also the agreement, disagreement between consecutive posts, right? So it's likely that people are going to disagree, but because, people tend to only jump in when they want to disagree, but we want to kind of like predict this model. Sometimes you have someone kind of like backing up someone else. So we have all of these different decisions, and then they have to be consistent, right? So if you're predicting that they're both going to be against the topic, then and they're consecutive, then they both have to agree. So these are kind of like the dependencies that come into play when doing something like this. In
Maria,
addition,
just to clarify that the agree versus disagree, it's like not that one comment disagrees with the other comment, but that one comment agrees with the central thesis and the other comment disagrees with the central thesis, right?
So with the central thesis is what we call pro and con. And agree and disagree, we talk about consecutive posts. So so if they to agree with, so if they agree with each other, then they both have to be con, for example.
I see. So you're labeling like the nodes and the edges.
And the edges, correct.
Yeah,
so in the end, it's a true prediction problem. That's why we call it structured. And in addition to that, we are going to talk about, we talk a lot about the context, broader context. So we are also going to model the users and not just the text. So the users have some attributes, they have some profile information that we're going to consider. And they also have relations between each other, right? So is this kind of vote information that I talked to you about. So people come and maybe they don't participate in the debate, they don't say anything, but they cast a like to some post, and then we can also derive inferences from that. So this is the task, and the only thing we know is the topic, the posts, the users, and we are going to assume that we know the structure of the tree. So we know who responds to who, but we don't know whether they agree or disagree. So the evaluation plan here is to compare to other modeling strategies. One that we talk about is local versus global. So whether you consider the dependencies or not, right? So if you just do this like predictions separately, or you kind of like consider them together and consider the dependencies and the constraints. Then we're going to evaluate ReL nets. If you remember, this is this kind of like relational embedding space that I talked about. So this idea of reusing parameters for the same types of entities and relations across different rules. And then we're going to do some qualitative evaluation on the representation, learning, and interpretability of our learned model. And then we're going to compare to other methods. One is just end-to-end neural nets. So this is just, kind of input, neural net, output. Relational embedding methods are methods that kind of do the ReL net portion of it, but they don't do the structured inference portion of things. So they try to learn, entity and relation embeddings that are shared, but they don't really enforce consistency or perform any type of symbolic inference. And then we're going to compare to other probabilistic logic frameworks, both purely symbolic. So people that, just live in the frameworks that live in symbolic land and don't really learn any neural nets or any embeddings. And then other Neural-Symbolic frameworks out there. But the main drawback between these methods that are out there is that they do not provide a way to update the base classifier or the base representations. So this is what we kind of bring to the table. This is kind of the general results that we have. So just to kind of parse this, post, user, and voter is the prediction of post is going to predict whether a post agrees or doesn't agree with the main thesis. So the pro-con stance at the post level. Then we predict that at the user level as well. And then we're also going to measure whether we can predict the voting relations. So whether two people are likely to agree with each other. And then this numbers are F1 score. So it's just kind of to account for imbalances in the data. This metric kind of does that so that if you have way more people agreeing than disagreeing, then you're not going to be biased by the metric. And then this yellow part, these are just independent neural nets. So just, text neural net to output or use of neural net to output. So no dependencies, no shared representations. Then these green ones are these relational embedding methods. We use 3 really popular ones. They learn entity and relation embeddings. And then the blue ones are probabilistic logics. PSL is a purely symbolic one. So it's very similar to ours, but they only learn 1 weight per rule. And they don't have neural nets to learn that or any representation for entities and relations. And then TensorLog is another probabilistic logic. They are also a neural-symbolic model, but instead of putting the neural part into learning to represent entities and relations, what they do is essentially try to frame the inference as a differentiable operation and then use a neural net to learn it. But everything, all the representations are symbolic. And then these orange ones is our framework. We have 3 versions. One is joint inference. This means, this means that the symbolic inference is done only at prediction time and not during learning. So basically you just learn independent nets like this yellow one, and then just combine them at prediction time with inference. The global one is the method that does do the inference, derive the structure laws, and propagates back to everything. And then the ReL nets version is the one that also shares parameters across, like represent the entities and relations in all the rules using the same parameters. So the trend is kind of what you would expect. So symbolic inference is the winner. So that's why blue is way better than green. So representing dependencies is what gives you the most edge. But then by combining, also learning to represent things in an embedding space, you can gain some performance here. The performance seems low in NLP land. This is pretty huge when you move, kind of like a little bit above. These are all statistically significant. We did some tests, so we can kind of like be sure that there was some type of improvement. So apart from that, we wanted to, we have all these claims of this being more explainable, more interpretable, and so on. So we wanted to see whether that was true. So we wanted to evaluate our representations as a way to look under the hood. So we're going to go back to this kind of operators that I talk about, moving between, raw and symbolic representations by mapping statements to meaningful symbols or learning meaningful embeddings for symbols. So this is kind of the test that we do. So we took statements made by people in the debates in the context of guns, and we tried to look at the symbols that had the highest scores. In this case, this symbol was an ideology. So we could kind of recover things like statements where we talk about gun laws not being good for anything, being ineffective and shouldn't be passed because of the right to bear arms, had higher scoring symbols for, higher scoring for right-leaning symbols like conservative or moderate-leaning conservative. And then things where you talk about gun control being good for society or some type of gun control being used had higher scores for moderate and left symbols. And then we also looked at the embedding of symbols themselves. So if you remember, we're going to learn a distributive representation for symbols as well. So we have a vector for the symbol liberal. We have a vector for the symbol conservative. And then we have a vector for statements made in text. And what we do is try to see which statements are closest to the ideologies in this space by using something like, I don't know, like cosine similarity or something like that over these vectors. And we could recover interesting things. For example, statements closest to the idea, the liberal symbol in the context of LGBT issues were supportive statements where legality was emphasized. Whereas for the conservative symbol, we found both supportive and opposing statements, but in most cases, morality was emphasized. So things about, things being good or bad, moral or immoral, taboo or sin, were like closer to conservative than they were to liberal. So now this is kind of cool, in having a model like this. Now you have some symbols, you have not only have the weights that you have for each rule, but now you also have some distributed representation for all the elements in your program. So you have vectors for text, vector for users, vector for all the symbols that introduce like ideology, stances, and so on. And now you can see whether you learn anything meaningful. And this is a way to kind of see what your model is learning. So disclaimer, this doesn't necessarily need to be okay. It's like, it's just basically a way to see what the model learned. And in some cases, you can kind of see the patterns that are being captured. And it's better than just having kind of just the output and then try to know whatever is going on under the hood in your neural net. Then we took it a step further and see if this kind of like would translate to what we call out of domain data. So the previous test was on text in the same debates that we learned over, right? So we just took some debates that we were training on and then took some of the portion of the test set and try to look at. But then do these concepts or these representations generalize? So what we did was downloaded statements by 3 prominent politicians from some web page called On the Issues. So we downloaded statements from Sanders, Biden, and Trump, and then we tried to score them using our model. And this is on the left-hand side, you can see kind of like the aggregate results. So while there is some error and some variance, on the aggregate level, we were able to kind of recover this kind of like political spectrum. So you have Sanders leaning mostly left, Trump leaning mostly right, and Biden leaning left, but somewhere in the middle. So you can kind of recover kind of the spectrum that you would assume. And on the right, we have some examples of the issue statement and label that we were able to recover using our model. And one interesting thing was, for example, in the cases where the statement prediction wouldn't necessarily align with what you would expect from the politician, in some cases, we thought by evaluating this, that the model was actually correct. So for example, you have in cases of Trump, a statement that he made prior to running for office, where he was, talking about being pro-life, sorry, that's not the one. Talking about being like pro-choice and talking about Planned Parenthood doing great work on women's health, and we were able to, like classify that as left, which makes kind of sense based on like the broader views of the parties. So there's some noise, but there's also some kind of like nuance being captured into the model. So this is kind of what I have for this talk. So to summarize, we motivated a neural-symbolic approach for natural language tasks involving long text and contextualizing information. We introduced a general framework to support that and obtain models that are easy to interpret and expand. So thanks everyone. And I'm happy to hear what you have to say.
Awesome. Thank you very much, Maria. That was terrific. Why don't I start us off with a question, and then anybody else who has questions, please just unmute yourselves and ask, and we'll do our best not to Zoom trod all over each other. So this last point is kind of interesting at a philosophical level about the NLP maybe being better than our own intuition at classifying the spectrum of beliefs. Are there maybe more technical applications where this would yield, I don't know, interesting statements about differing views that are not, I mean, politics are one thing, but are there like differing views on technical subjects that that you can apply this type of technique to?
I think this technique is kind of suitable to anything where you want to model kind of a concept or repeating things and structure and dependencies. So it's like things that we work on are a good candidate as well, right? So you have kind of like a structure that when we're predicting this type of trigger constraint kind of structure to tie these dependencies are true. Everyone's working a lot on the political domain is a kind of like what people are into right now, but there's this kind of things are also used on a lot of like what they call medical NLP. So when they have papers or kind of like documentation talking about how like some drug is working, how it's effective, what things kind of like interact with each other. I think these are also suitable techniques.
Very cool. Thanks. I'll open the floor. Alex, you've got a question?
Yeah. So how good is the stance prediction at uncovering like hidden variables, hidden constants, I guess you'd say, but unstated implicit beliefs?
Yeah. Yeah, you can. You can also explicitly model those if you wanted to. So let's say, I mean, they're not necessarily going to capture what you want them to capture, but you can, this symbols or these relations don't necessarily need to be observed or learned from data. You could have like a latent kind of like variable that you're expecting there. So I have this predicate, it has like, I don't know, 10 possible assignments, and then you're going to map a dependency between that and a prediction. So you could, like map statement to latent variable to stance. And then I just kind of like let the model learn the assignment and then look back and see what kind of things you're capturing in each group. So it's kind of like a proxy for like a clustering style technique that is more structured, because then you can define constraints over those. And then you can kind of recover hidden information. It's the thing with like this type of models is that you might have some intuition of what you're going to capture, but that doesn't necessarily translate. I think that's when like being able to constrain it comes into play, because you can then say, you have some domain knowledge about it. So you can say things like, oh, if they're talking about a particular entity in like a bad light or in a good light, you can kind of embed this knowledge into it. But then there's this like game of like, like how much bias, you put into the model. It's never going to be perfect. I don't think where you're modeling this like type of complex domains, but there's definitely something that you can capture there. We are actually working on that right now. So in this paper, everything was learned from data. But our next step is to actually model hidden non-observed variables and then try to see what we can recover from that. That is like one direction that we're looking at.
But you still have to like almost manually know what to look for there. It sounds like it.
Well,
Like domain specific stuff.
yeah, if you want to constrain it, then yes. But if not, you can just say, oh, I just map this statement to a variable. The only thing you need to know is how many instances of that you want, right? So if you want, you can model the number of hidden variables, but if they're discrete, then you do need to know the number. But other than that, no. And then you can play with it, right? So you can put it as like 2 and then expand to 15, depending on how many you want to capture. But then you don't really need to constrain it. And then you can kind of like just see what comes up by your model. But constraining it would help you, introduce bias if you do want to. So because sometimes I think there are 2 types of hidden information, right? The one that you just want to discover, you don't know what is there. And then there's the ones that are there, but you don't have supervision for them. So it's like, oh, I know this is something that I want to capture, but I don't know, I don't have data to learn it from. So then you can kind of bias your model with constraints to recover that. I don't know if that answers your question at all, but.
Yeah, it answers it in that there isn't a simple answer, I guess.
Yeah. Yeah. But yeah, I mean, it's pretty, I think, hard, right? Because you can never model everything, especially when you're talking about kind of like this like abstract concepts. One thing that we've looked at is into adding symbols for kind of like psychological or political theories that are out there. So things like moral foundations, for example. So, oh, I'm gonna try to model morality, fairness, this kind of type of things, and then kind of write these rules. These are weighted rules, right? So they don't need to be always hold true. So you can recover, for example, when people talk about morality in the context of abortion, are they likely to be Republican or liberal? This kind of things you try to recover. And so capture some uncertainty on them.
Can you make structural comparisons of how different types of people argue? Like people on the left argue using one type of kind of symbolic structure of argument, and people on the right have a different structure to the way they think, or something like that.
That'd be really cool, actually. I think that's something to consider. So it's like how people construct their arguments. Do they vary across like political?
Yeah, because you already kind of have graphs, right?
Yeah.
Like you showed us, you're guessing these weighted graphs of argument, which makes me want to compare graphs.
Yeah, I think that'd be interesting to know. And actually that can also not only across political lines, but like maybe across platforms, right? So the way a politician is going to talk is not the same as like some influencer on Twitter, trying to sell you some idea. I think this might be interesting to capture. Yeah, no, definitely. Good idea.
I've got a quick question about how the text is interpreted by the system. So I guess, would you imagine that it could be swayed if you're comparing discourse from different platforms? So to give an example of this, you would imagine that if someone is talking in a debate, the grammar of their speech is not going to actually be correct, even if their argument is perfectly coherent. But if you compare that to something like a written form, where it's going to be complete sentences, periods, commas, all in the right place, do you find that the system is influenced by the actual grammatical structure of the text that it's fed into?
Yeah, this is very prevalent in NLP. So usually things don't translate well. So if you have something trained on news data, then it doesn't work on social nets. Or if you have something learned on news articles, then it doesn't work on technical documentation. So that this is prevalent and it's going to happen. In this case, you can use kind of symbols. If you have enough like samples from different types of sources, then you can use symbols to kind of ground that. So if I have samples from like, right-leaning arguments from news sources, but I also have samples from right-leaning arguments from, Twitter, Facebook, whatever, Reddit, then you can maybe learn to generalize better and kind of omit the stylistic differences. But if you don't account for it, that definitely that's going to show up.
Okay, thank you.
Yeah, no problem.
Another follow-up. Do you have any hypotheses on why voting seems to be so much noisier than argumentation, predictably?
Yeah.
Like just small network effects or...
It's a pretty small network. So when we look at voting, we look at just like networks inside a particular debate. So you're just going to have a handful of votes. And it doesn't really, it's like a hard problem. I think if we had like more samples, or if you were to model maybe other types of relations there to like, I don't know, friendships in like the friendship graph of the social net, and then tie that to voting, yeah, that might help you there. But yeah, it was pretty small in each, and we treated it differently. So we didn't connect different debates to other debates, which is something you could do. We model each debate in isolation, so that could also make it harder. They're also like, I looked at the data and some things are pretty noisy, right? So I think some people also like troll around, and they are going to vote for something that doesn't really align with the things they're saying in other places or what they have in their profiles. So that does happen. But an aggregate, yeah.
Speaking of that, how do you account for, disingenuity on the textual level?
We don't, but that's a really good thing that you should like take into consideration if you were to deploy this anywhere. Yeah. Yeah, the
Alex,
people always trying to hack the system.
Somebody posted in the Tucson subreddit recently, very earnestly asking what the best romantic dinner is in Tucson. And I said the EG's parking lot. I said the EG's parking lot. So the somebody who's trolling would be me.
Well, so that's the thing. You could probably, add that to a user vector at some level.
Yeah, and you can,
exactly.
You can try to model that for sure. And you have also kind of like this devil advocates people. So you're going to have someone that, in their profile, they're like completely Republican or completely liberal, and then they want to argue the complete opposite view. So that's something that definitely does show up in this type of, this was like this domain was some webpage called debate.org that we use, and they have this kind of like structured way of creating arguments. So they have like this rounds and two people debate, and even in that space, people troll around, and yeah, you'd be surprised. I mean, I was surprised that people even engage in this type of things. It's like they just go online to debate some topic, but they do.
Can you see a difference? Oh, I'm sorry. Go ahead, Neha.
I'm sorry. I had more of a technical question. So when you find the sentence that's closest to a concept, do you look over the set of all possible sentences in your database, and you look over all the vector constructions?
Yeah. Okay. So that one was kind of like a rank. So we like just showed you the top ones.
And how do you construct the vector for the sentence embedding? Is it based on the words themselves?
Yeah, so that's kind of like, in this model, kind of you have a neural net that represents each of those entities and relations. So for like the text, we have a specific neural net there. We use the BERT, which is a transformer model. So a transformer model kind of like uses the sequence of all the words, and then they create kind of like all possible, they have like what they call an attention layer. And so they look at all possible mappings, and then they have like some self-assignments there. So the idea here is that, it's kind of like an abstraction. You can plug in your favorite neural representation there, and kind of play with that. We use kind of what was best performing right now. Yeah. So yeah, based on the sentences, and BERT is contextualized. So you're not going to have a single embedding for each word. The embedding for each word is going to be dependent on the words that are nearby. So, the bank is going to look different, whether it has like money things around it, or, the park and you're sitting on a bench kind of thing. Yeah.
Okay, that makes sense. Yeah.
Maria, do you think you would get very different results if you did this in other languages like Spanish or Chinese? And if so, how would it be different?
Yeah, I think so, particularly because, the underlying models that we use to kind of build these building blocks were built around English. So they're better on English. So I expect the performance to be worse just because of that. But they, if you do like find some good model or something, they're usually kind of I don't know about Chinese. I can't speak to it, but in Spanish, there are other issues that are going to come out with the way people construct arguments is different. We might need to like kind of like have a specific model. And then also, if you're modeling politics, then you gotta kind of have to model the politics that are local to each particular discussion, right? So in this case, we were using liberal conservative symbols, but that might not translate necessarily, to China.
Right, or they mean different things.
Yeah. And they mean completely different things. So you might need to have your own left-right models for each kind of region, because they're gonna be different. But that'd be pretty interesting, to say, kind of see how that moves.
I'm more thinking of in Spanish, like I'm reading this book 2663 or something like that. And it just seems like in Spanish, like people just like write a whole book with no periods, and then they put the periods in wherever the fuck they feel like it after the fact. And they have like a budget of 10 periods for the whole book, as far as I can tell. It's just astonishing. And I've had this experience with other authors in Spanish before too, that the end of the sentence is a purely optional thing, but it's also implied if you don't put it there. And it seems like that would make it pretty hard, because you'd have to like have some way to figure out what are actually concrete thoughts that are
I think partitioning,
I mean?
is probably harder. And I mean, that's funny, right? Because it happens to us when we first start learning English, and we write this like huge paragraph with not like separations.
Exactly.
And then you need to learn to break down the sentences. So that's that common mistake. I think that probably you need kind of like a good partitioning mechanism there. We do it at the post level, so we don't really deal with that very much. But if you were doing it at the sentence level or like at the statement level, then that might be.
I feel like the author just kind of did the Salt Bay thing with periods. And
it makes sense to me, but I can understand that it doesn't make sense to people. And the comments, it's really different, I think. And Spanish also kind of like, you say more, you just talk more to make the same point, right?
Right.
No, definitely. And languages like Chinese or Japanese, then they have an additional layer of complexity, because their symbols are very rich in semantic knowledge, right? So it's not necessarily just the word form, but you also like the symbol. It's the symbol of water combined with something else. It's like completely different challenges in NLP when dealing with those type of languages.
Sure.
I feel like if you could train PyTorch from the ground up, German would probably be the best implementation language for it, just because it's so compositional and regular.
It could be. You got this like composed words are pretty awesome. I'm trying to come in.
Oh, we've got Alberto.
Look at that. No, definitely. And that's like it's a trending topic right now, right? Because most of the advances the field has made are very English centric. So there's a lot of kind of like recent interest into making that more accessible to other languages.
So for inference-based approaches, did you ever have issues with like applying too much consistency? Because whatever the horizon effect of your model is, it's probably actually better than it is for human thinkers.
It does happen. We kind of work in this land where like structure helps us, but that might not necessarily always be the case. So you do have cases like we were working on a problem where we were kind of like modeling this like framing devices and moral foundations, and we wrote these constraints to be like, this types of framing devices go with this type of moral foundations, and they have to go together. And we were expecting that to be like, this is going to improve this model so much, and it totally broke our performance. So it's sometimes things that you'd expect, if you get like try to enforce them too hard, then they don't. The good thing about framework like this is like it lets you kind of play around with the dependencies that you would like to represent, so you can kind of like add and remove as it works best. And as I see this, like,
could you reverse engineer the moral foundations from the arguments that somebody makes in an automated fashion?
You can totally I think, and they're very tied to stance, at least in like highly polarized topics. Maybe if you were to look at topics where, I don't know if there are any non-polarized topics like recently in American politics, but if you can find one, then that might not necessarily translate. We were trying to look in for examples of something like that to demo something. So if you can think, if any of you have ideas of something that might not be too polarized, then that'd be
I mean, you could do academics, right? Like you could look at some academic topic that's completely apolitical, like some academic debate where people are kind of open to both things.
yeah, I don't
something
know
really
like
boring.
how much moral foundations like play into something like that, not necessarily. Maybe if you're talking about like academic integrity or something like that.
I'm thinking of like a comparison between two equally boring but likely conjectures in string theory, something like that, where like no one really cares, but
Yeah,
but
there's some
they'll
liability.
they'll put some effort into it.
I feel like in those cases, though, like the funding politics is just as polarizing as partisan politics in some ways.
It could be. Yeah.
But no, that would be something idealized like that.
I would also argue if you find someone nowadays arguing about string theory, chances are they care a lot about it. So,
Yeah. Cool. Well, Maria, thank you for talking to us. This was a lot of fun.
No, thank everyone.
And I've gotten some messages already from people saying that they missed the talk, but they'll listen to the recording afterwards. So it's nice that this one was recorded. And at some point in the future, as I said, I or someone else will come back to present our work together, which I'm very excited about, and hopefully will be finished sooner rather than later.
Yeah, hopefully.
So thank you again. We really appreciate it. And
thank you guys.
Yeah. And
Nice to meet you all.
Okay. Adios.
Bye.